Hello students, I am Dr. Alok Tripathi and I'll teach you today root of a non-linear equation. In this, we'll study bisection and regular falsy method. These are the prerequisites to understand the root of equation, analytical methods to find the root of an equation, continuity of functions and plotting of functions. So these three topics you should study before starting finding of roots of a nonlinear equation by bisection and regular falsy method. Our objectives of this lecture is to find the root of a nonlinear equation by bisection and regular falsy method. So in this slide we shall see what is the meaning of root of a equation. First of all, we are given a function fx and we need to find the root of fx is equals to 0. So root of this equation will be that value of x which will satisfy this equation fx is equals to 0. Means after putting the value of x, the function should become 0. So root of a function fx, it is a value a such that for which f of a is equals to 0. In the graph you can see here, this is the graph of fx, the given function, and it cuts the x-axis at this point. Okay, so means the value of the function at this point will be 0. So we can say that root of equation fx is equals to 0 is that value of x from which the graph of the function cuts the x-axis. Now see one example. We are given a function fx is equals to x square minus 4 and we want to find the root of this function. Therefore we will put fx is equals to 0. So x square minus 4 equal to 0 will give us x is equals to minus 2 and x is equals to 2. These two values of x will satisfy the equation fx is equals to 0. You can see if you put x is equals to minus 2 here, so this will give you 4. 4 minus 4 becomes 0, and for again x is equals to 2. If we compute this, then this 2 square becomes 4 minus 4 again it is 0. Okay, we have put those values in the function and we get 0. Therefore x is equals to minus 2 and x is equals to 2 will be called the roots of this function x square minus 4. Now see the intermediate value property. What is it? If we have a continuous function fx defined on an interval, closed interval a comma b, and f of a means the value of the function at first endpoint of the interval and the value of the function at the second endpoint of this interval. If these two values means f of a and f of b, these two values are of opposite signs, means if f of a is positive then f of b should be negative. If f of a is negative then f of b should be negative. Positive. Then there is a value c in this interval between the points a and b. There exists one value c such that fc is equals to 0. Means if a function is continuous in a closed interval ab and f of a and f of b are of opposite signs, then there must exist one root of the equation fx is equals to 0 in the interval a comma b. You can see the graph here this is the plot of our function fx, this one. Now this is our interval a to b, this is our closed interval. At the point a you can see f of a is lying under the x-axis, therefore the sign of f of a will be negative. And at the end point b, the value of the function f of b is lying above the x-axis, therefore it becomes positive. So f of a and f of b both are of opposite signs. It means, and since if function is continuous in an interval a to b, then at every point between a to b the function is defined and give some value at all the interior points in the interval. So from f of a to f of b all values will be included, and when we move under the x-axis towards above the x-axis, then the graph of the function must cut the x-axis. So this point will be called a root of the equation fx is equals to 0, or you can say root of the function fx. This is intermediate value property. Now I will tell you what is bisection method and why do we need this. Suppose we are given an equation fx is equals to 0. If it is a polynomial equation of order 2 or 3, then we can easily find the root of this equation by well-known methods. These methods are called analytical methods. But what will happen if we take any equation which is including any transcendental function? Then what we will do? Suppose we are given an equation cos x minus x e to the power x is equals to 0, and we want to find the root of this equation. Then we cannot apply any well-known analytical method to solve such type of problems. We use numerical methods, and first type of numerical method is bisection method. So what is bisection method? It is a successive approximation method that narrows down an interval that contains a root of the function fx. Means first we have to find the interval which is containing the root of the function fx. There we can apply the intermediate value property of continuous functions. Bisection method is given an initial interval a to b that contains a root. So here we are applying the intermediate value property. We'll check the value of the function at a and value of the function at b. We have to check the sign of these two, sign of f of a, sign of f of b. If the sign of f of a and f of b is opposite, then we can choose that interval because it will contain the root. The surety comes from intermediate value property. So what will bisection method do? It will cut the interval into two halves and check which half interval contains a root of the function. Suppose we have any equation fx is equals to 0, and we have found that the root of this equation is lying in the interval 0 to 2. So when we apply bisection method, it will cut the interval into two halves. Means we have two intervals now. First interval 0 to 1, another interval 1 to 2. Now again we will check the sign of the function in the first interval and for the second interval. Now it will tell us in which interval. We have two intervals now, 0 to 1 and 1 to 2. It will tell us that in which interval the root of the function exactly lies. The bisection method will keep cut the interval in halves until the resulting interval is extremely small. Means we have to apply bisection method until and unless we get our root of desired accuracy. The root is then approximately equal to any value in the final, or you can say very small, interval. Now see the procedure of bisection method through the graph. Suppose we are given a function fx and the equation fx is equals to 0. Now we have chosen the interval a to b. F of a is the value of the function at first endpoint of the interval, and f of b is the value of the function at second point of the interval. F of a and f of b. We can see here f of a is lying under the x-axis and f of b is lying above the x-axis. Therefore, sign of these two will be opposite. Since fx is a continuous function, therefore it will cut the x-axis 100%. Then that is actually the exact root of the equation fx is equals to 0. So we have chosen the interval a to b. Now we'll apply the bisection method. What it does, it just cuts the interval into two parts, two equal parts. So we have done here a plus b by 2, a plus b by 2. This will give you the value, middle value, and we are denoting it by m. You can see here m is equals to a plus b by 2. So this is the mid value of the interval. Now what we do, we have the value of the function at first endpoint a. Again we have the value at second endpoint of the interval. Now we'll check the value of the function at this midpoint of the interval m. We have calculated and it will be the value f of m. Now we can see here f of m is a positive value since it is lying above the x-axis. Therefore it is a positive value. F of a was negative, therefore it means our interval is shrink now. You can see we have two intervals here, interval a to m and m to b. Now can we choose the interval m to b now? No, because at the value at the midpoint m, the value of the function is fm, and at the endpoint b, the value of the function is f of b, and both values are positive. Since both values are positive, therefore we cannot guarantee that the root of the equation fx is equals to 0 is lying inside the interval m to b. But for the second interval, interval a to m, f of a is negative, f of m is positive, means our interval will be a to m. In this figure, we have just shown what we have known earlier, that f of a is a negative value, m, the m at the value m, value of the function is positive, therefore our root of the equation fx is equals to 0 will lie inside the interval a to m. Means earlier we have taken this interval a to b, but now our b will coincide with m now. Means we have to change our b to m. Now we are giving one example here. So suppose we are given equation, or you can say function fx is equals to x square minus 3. So we already know that the root of this function are the root 3 and minus under root 3. But we want to find the root of this function by numerical method, means bisection method. So first of all we shall find the interval in which the root of this function will lie. So uh, how we can do it? We'll apply the hit and trial method. So starting from 0, first we'll put the point 0. When we put 0 in this, we'll get minus 3. Okay. For x is equals to 1, next value we shall put x is equals to 1 here. So 1 square minus 3, the value is minus 2. Again a negative value. At the point x is equals to 0, we have got a negative value. Therefore, we have to find that value of x for which function becomes positive. So f of 0 is equals to minus 3. Now fx is equals to x square minus 3. So at x is equals to 1, we have checked that it is given again a negative value. So we cannot consider 1 because we have not guaranteed that the root of this function will lie in that interval or not. So for x is equals to 2, we'll get f2 is equals to 2 square minus 3. f2 is equals to 2 square minus 3. So 4 minus 3 becomes 1. This is a positive value. For x is equals to 4, you can see 4 square minus 3. This becomes 13. f of 4, it is 13. So here we have taken the interval 0 comma 4. If you want to choose, you can also choose 0 comma 2 because at the point 0 value of the function is negative, and for x is equals to 2, the value of the function is positive. So you may choose also the interval 0 comma 2. So we have got our interval, closed interval 0 to 4, and now we shall apply the bisection method on this interval. So m is equals to, m is midpoint of this interval, we can find it by applying a plus b by 2. So we'll get here 2. Our midpoint of this interval is 2. Now we shall check the value of the function at this point. So fm is equals to f of 2. When we put x is equals to 2 in x square minus 3, then we will get fm is equals to 1. It is a positive value. Now we already know that f of 0 is minus 3, which is a negative value. F of 4 was 13, it is a positive value. Means if you see this figure, at 0 the value of the function is lying under the x-axis. The value of the function at x is equals to 4 is lying above the x-axis. It is a positive value. And at the midpoint, that is at x is equals to 2, we have the value of the function is again lying above the x-axis, means it is a positive value. Therefore, our interval of interest will be now 0 to 2, because this is intermediate value theorem guaranteeing that root of the function fx x square minus 3 will lie in this interval. Now we have found our new interval, which is 0 comma 2. Again we shall apply bisection method on this interval. After bisecting this interval, we get the midpoint as 1. Now we have checked the value of the function at this midpoint fm. This is equals to minus 2, which is a negative value. F of 0 was negative, f of 2 was positive. Means at 0 we have a negative value, and at 1 we have again a negative value. Therefore our interval of interest will be 1 to 2. Means 0 to 1, at both these points the value of the function is negative, means these are of same sign. Therefore intermediate value theorem cannot be applied here. But for x is equals to 1, we have the negative value of the function, and at the end point 2 we have positive value of the function. Therefore we can apply intermediate value theorem, and it will guarantee that the root of this function will lie inside 1 to 2. Now our interval is 1 to 2. Again we are bisecting it. We get the mid value as 1.5. We have checked the value of the function at this midpoint. The value is negative. At x is equals to 1, the value was negative. At x is equals to 2, the value was positive. Therefore our interval of interest will be 1.5 to 2. Okay, now we can see here that the interval is getting shrinked. We are bisecting the interval, and every time the length of the new interval is smaller than the previous one. Now we shall continue this process until and unless we get the root of our desired accuracy. What we have seen that interval gets smaller and smaller, but it will always contain the root 3. Whatever interval we have used or we have bisected, that is containing the root. Now when the interval is smaller than this quantity, actually this quantity is not fixed, this is up to you. When the size of the interval is smaller than 1 upon 2 into 10 to the power minus n, we shall end our process. What is n here? N is number of decimal place. Suppose we want to find the root of a given equation correct up to 3 decimal places. So it means the size of the interval should be less than 1 upon 2 into 10 to the power minus 3. So at that moment, the end point of the interval will be very close to the root 3. Now we move towards our next numerical method to find the root of a nonlinear equation. This method is called Regula falsi method. This is also known as false position method or method of chords. This method has 3 names: Regula falsi, second method of false position, and last method of chords. Again we are considering the equation fx is equals to 0, and we have found two values a and b such that f of a and f of b are of opposite signs. We let here a is less than b. Now the graph of y is equals to fx will meet the x-axis at the same point between a and b. Therefore, the equation of the chord joining the points a comma f of a and b comma f of b is y minus f of a divided by x minus a. This is equals to f of b minus f of a divided by b minus a. In the same interval, small interval, a comma b, the graph of the function can be considered as a straight line. That is, in this interval a comma b, we are replacing the original function by a straight line, so that x coordinate of the point of intersection of the chord joining a comma fa and b comma fb with the x-axis will give an approximate value of the root. Putting y equals to 0 in the equation, we get minus fa divided by x minus x1 equals to f of b minus f of a divided by b minus a. Now x is equals to, this will give us a minus fa divided by fa minus fb minus fa into b minus a. So x is equals to afb minus bfa divided by fb minus fa. This is our first approximation to the root, and it is denoted by x naught. Now we shall check the value of the function at this x naught, and we will decide whether our root is lying in a to x naught or x naught to b. F of a and f of x naught are of opposite signs. Then the root lies between a and x naught. Therefore our interval of interest will be a to x naught. Now taking this interval into consideration, a to x naught, we will find our next approximation to the root. This is denoted by x1. Now we will apply this method repeatedly till we get the root of our desired accuracy. Now the geometrical interpretation of regular falsy method is described here. You can see this is our original function fx. This one. This is our original function fx. Now we have considered the interval a to b. The q point is our exact root a to b. First we have checked the value of the function at a. It is afa, and at the point b, for x is equals to b, the value of the function here we can see it is negative, and at x is equals to a, the value of the function is positive. Now we shall draw a line joining the point a and b. This is our straight line. Why we have joined this? Because I have told you earlier that we have to replace our original function by a straight line. So this straight line is replacing our original function. Now where this straight line AB cuts the x-axis, this is our first approximation to the root denoted by x0, this one. So from this point x0, we draw a perpendicular line to x-axis, and where it cuts the graph of the original function, from there we join the endpoint A. Now we have another straight line A to this point. It means again it will cut the x-axis, so this point will be our next approximation to the root. We will continue our process till we get the root of our desired accuracy. You can see first straight line was far from the point Q. When we have taken the next approximation, x1 is closer to the root. Next approximation x2 is more closer to the root, and we repeat this process. Then we get our root, which is very close to the exact one. Now see this example. Find an approximate value of the root of the equation x cube plus x minus 1 equals to 0 near x is equals to 1 by the method of false position using the formula twice. Means we have to apply a regular falsy method 2 times, and one point of the interval in which the root of the given equation is lying is given to us. So by hit and trial method we shall try to find the another point of the interval. So we have put here x is equals to 0.5. This is our function x cube plus x minus 1. f.5 is equals to minus 0.375, which is a negative value. And at x is equals to 1, we can see here 1 plus 1 minus 1. So we'll get 1 here, means we have a positive value. So our interval of interest will be 0.5 to 1. Now we shall apply the regular falsy method to find the first approximation to the root of the given equation. X0 is equals to AFB minus BFA divided by FB minus FA. After putting all these values, we are getting here 0.64. So f of 0.64, this is equals to minus 0.0979, which is a negative value. Therefore, we can say that the root will lie inside the interval 0.64 to 1. We have already seen that x is equals to 1. The value of the equation was positive, and we have just found that value of the function at x is equals to 0.4 is negative. Therefore, our interval of interest will be 0.64 to 1. Now we shall again apply the formula of regular falsy method, and we get our next approximation to the root denoted by x1. After putting all these values, we are getting here 0.672. Now in this question, we are forced to apply method of false position only twice, but sometimes we have to apply regular falsy method to find the equation of a root till the desired accuracy. Okay, so today In this lecture video, we have learned how to find the root of a nonlinear equation by numerical methods. The two methods we have discussed today. First one was bisection method, in which we have bisected our interval repeatedly, and next is regular Palsy method we have applied. So thank you very much for your patience.